Okay, so we had the maths from the lecture on Tuesday. I'm happy we had a class today. Had there not been so much awesome snow out there, we would have gone through that a little bit more to get you a bit more familiar with it. You may not be happy with maths, but it's a really good way to formalise arguments and think in more concrete ways about things that we're interested in. So what we'll do is we'll talk through this Szymanski model, looking at competitive balance with a really small sports league. You may recall it was slides 25 onwards, slides 25 through to 27 in the lecture, and it was a two-team league. So you have two teams. We think about these as Team 1, Team 2. And then we think about their utility function, or fan utility of these teams. So we had U1, utility for Team 1. Well, that's some function, mu1 multiplied by W1, where W1 is the win ratio. I.e. how many of the games, or what percentage of the games Team 1 wins. There's two teams in the league, so therefore, if we think about percentages or proportions, W1 plus W2, percentage of games that Team 1 wins and Team 2 wins, must equal 1. Okay? So, that's going to help us a little bit later on. In addition, what the model assumes, so it is very simplistic, but it still helps to make points. It assumes that the win ratio is equal to the talent on each team. So T1 is talent on Team 1. And so the win ratio, as is set out, is T1 over T1 plus T2, i.e. the proportion of talent in Team 1 relative to the total amount of talent is how much Team 1 wins. Okay, so we have a utility of Team 1, or the utility of Team I, we sometimes will write, just to be general, utility of Team I, mu I wi, which is then equal to mu I ti, because we're making I equal to 1 in this case, over T1 plus T2. And we then say, well, I can be 1 or 2 for Team 1 or Team 2. So utility of Team 1, some function of the talent, but also this mu thing. Mu is this fan intensity. So mu I would be fan intensity for Team I, Team 1 or Team 2. I use the example in the lectures, somewhat stereotypically, of Millwall and Everton. We might think about you might think about a different sport. You might think about your own country. There's all sorts of different examples of this, and there's probably different ways in which we could measure it as well. You might measure it by the number of fans turning up. You might measure it by some kind of social media presence. All sorts of ways of measuring it. The point is, there's some fan intensity, which means that for the same win percentage, that some teams will get more utility from the same win percentage because their mu is higher. So we might say mu1 greater than mu2 if Team 1 fans more intense. So then their fans get more utility from wins than fans of other teams. And I said in my example that Millwall fans, very passionate fans. You might also attribute the same thing to Leeds United fans as well, kind of stereotypically passionate fans, whereas fans of other clubs, Everton, so stereotypically, I know plenty of friends who are Everton fans, plenty of friends who are Man City fans, who are anything but passionless, but nonetheless this is the stereotype. And so there's more utility gained if these teams win than if other teams win. And then we had this idea, two different ways in which we could organise the league. We might have, so I am left-handed, so I smudge everything. We might have one, some kind of social optimum. And then the other outcome would be just simply the competitive outcome. Competitive outcome, that is profit maximizing. The social optimum, we think about that as being utility maximizing, say. And that means we have to have some kind of utility function, but then we've got some kind of utility function up here. Okay, so that's quite useful. So let's skip on to the next page. I'll take photos of these pages so that you don't have to worry too much about missing material. In fact, I could potentially even move this over and leave the last page just there so you can still look at the last page, should that be helpful. So the total utility function specified is u with no subscript, which is u1 plus u2, so the utility of some of the two teams in the league, plus what Szymanski calls a couch potato effect, but we can be a bit less, I don't know, what's the word, pejorative about fans that don't watch in the stadium. Fans that watch on TV, who care about a spectacle. And what that means is, well, they care about the product of these win ratios. Remember that W1 plus W2 equals 1. So therefore we could sub in, we could say, well, W2 is 1 minus W1. And so then this W1, W2 term is W1, 1 minus W1. When is that maximized? Differentiate with respect to W1. This is W1 minus W1 squared. With respect to W1, gives us 1 minus 2 W1 equal to 0. W1 equals a half, or 0.5. So if each team wins half of its games, that's when this function is maximized, when the league is really, really balanced. Okay? The league is really balanced. So that's great. Fans like it when couch potato fans who watch on TV, or neutral fans, they like it when the game is really balanced. Of course, fans of each team don't. Fans of each team would prefer to see their team win. But we said that we're thinking about some kind of social optimum, some kind of utility maximization. I mentioned in the lecture, this is the idea of you have some kind of a benevolent social planner. Benevolent social planner. It's kind of a quaint idea that economists have, and the simple idea is that yes, this kind of person never exists, but this is some kind of benchmark that we can compare where we are to. Okay, so let's do that. And what would the benevolent social planner do? He or she, of course, would maximize total utility. So they would maximize the total utility function. So maximize u, which is u1 plus u2 plus theta w1 w2. What is the social planner? What can he affect? Well, we figure that he can affect win percentages. Okay, so we maximize total utility with respect to the win percentage. Okay, so we need to get this in terms of win percentages. We've already done some of the work by working out by stating this this up here. W2 is 1 minus W1. We need to stick in what the two utility functions are. So they are mu1 W1 plus mu2 W2 plus theta W1 W2. So we're thinking about maximizing with respect to the win. The social planner can choose what the win ratio is that's optimal, what we'd all feel happiest with. But we want to choose with respect to the win ratio where it's one variable rather than W1, W2. So let's sub in, let's use the result up here. we should probably number all of the ones that we might make use of. This is good for referring back to things when you're doing any kinds of maths. So we should probably call this equation 1, this equation 2 over here. The generic function, we could call this equation 3 here. Then equation 4 is the utility function, total utility. Equation 5 is relating W1 and W2 to each other. Equation 6 would be where we've maximized, and 7. Let's do that for now. And then 8 and 9. But we're going to use equation 5 here. So we're going to write mu1 W1 plus mu2 1 minus W1, because that's what W2 is, plus theta W1 1 minus W1. We're going to maximize this with respect to W1. And set that equal to 0. So we're going to get mu1, W1 goes. Then we're going to get nothing there, that will be 0, mu2 will go. Leave us with just minus mu2. So I'll just scribble that out. Minus mu2. And then we've got this thing over here. We're going to have plus theta times W1, so that will be plus theta. And then you've got minus W1 squared, so that will be minus 2 theta W1. Okay, and we're going to set that equal to 0 because we're maximizing. We could check the second derivatives, but we'll leave that for now. And we want to rearrange this for W1, the win ratio. That's the thing that we're choosing. So what do we then do? We take over mu2 and mu1 over to the other side. And then we it'll be okay because we've got the minus 2 in front of W1. So the first step will be, we'll have minus 2 W1 theta on this side, and we'll take everything over to the other side. Minus theta minus mu1 plus mu2. Divide through by 2. Let's make it divide through by minus 2 and divide through by theta. Well, first of all by minus 2, so W1 theta is equal to theta over 2 plus mu1 minus mu2 divided by 2, and then now we can just divide by theta, and we get W1, the win ratio that maximizes utility, makes us all happiest, is a half plus mu1 minus mu2 over 2 theta. Okay, so let's just number a few more equations. We'll call that one 10 and this one 11. Okay, and as we thought about in the lecture, this has a few implications. I'm going to be moving this across and then moving this on. This form has a few implications. Not least it shows us something about, I'm still just about in the screen, there we go. Something about what couch potatoes or neutral fans think relative to the win ratio being a half. If you recall, we imagine that a win ratio of a half, teams winning half of their games may be the best thing, but actually it's not. You can see that if mu1 is different from mu2, so if mu1 is equal to mu2, of course, that then tells us that W1 star is a half. So fan intensities are equal to each other, mu1, the win ratio is a half. However, if team 1 has more intense fans, well then we've got the W1 star is equal to a half plus mu1 minus mu2 over 2 theta, which is greater than a half. So in other words, team 1 with more intense fans should win more often in a utility maximizing, socially optimal situation, because their fans are more intense. They derive more satisfaction from their wins. So let's let them win a bit more. Let's let Man United win a few more games than perhaps they do. It's an idea, and of course, conversely, if team 2 have more intense fans, the other way around as well, they would win more games. So there's a socially optimal imbalance in how teams operate. So it can be socially optimal to have competitive imbalance, one team winning more often than the other. That's the utility maximizing situation. Also worth saying that theta is on the denominator down here. Theta, which is the preferences of those neutral fans back in equation 4. So if theta is big, then there's more of a difference. Sorry, then this term is smaller. And the optimal win ratio is closer to a half. Okay, so the stronger the preferences of our armchair fans, the closer we get a win ratio to a half. So we can think about this in terms of what's happened over the years with the Premier League in England, where the amount of money being generated by television, not just Sky Sports in the UK, but also around the world, is so vast that it makes sense for the Premier League authorities to think about these neutral fans. This theta has been getting bigger and bigger over the years in the Premier League. And perhaps as a result, we may have seen slightly more competitive outcomes in recent years. No team has won the Premier League more than one season on the bounce for quite a few years now. And that trend looks set to continue this season. And in extreme, if theta was infinitely large, so it was massive, this term would be essentially 0, and again the optimal win percentage would be a half, despite the fact that regardless of what the relative preferences were of the two sets of fans. Okay, so that's the social optimal outcome. We'll put a line through that. Next we're going to think about the profit maximising outcome, the competitive outcome. And what we noted in the slides, so in the lecture slides, equation 7 was a profit function for team I. Profit function for team I was this phi, Greek letter, phi I, mu I, w I. What is that? Well, this is our utility. It's worth noting from the utility functions. If we look back at equation 3 there, it's the utility function mu I, w I, and this phi I is some kind of reflection of how much clubs are able to extract monetarily from fan utility, so via merchandise sales, for example, and other things that clubs sell. But then clubs clearly have to employ talent to do well, and talent has in this model a fixed cost C. It isn't the case that some players cost more than others. They're just all players, all talent costs C, fixed cost. Just makes things fairly simple. Now the tricky thing, the thing to do here is we want to profit maximise. So we're going to maximise, and what we've got to think about is what does a team choose? A team doesn't choose a win ratio. A team chooses its level of talent. So we're going to maximise with respect to TI. Okay. So again, we're going to differentiate this function. We're going to differentiate with respect to Ti. Now, the first term here, we might think it doesn't have any reference to Ti, but it does, because of course the win ratio is this fixed function of talent ratios. So mu I Ti over T1 plus T2. Okay. I'm going to differentiate that, and there's a bit of an issue here because we've got a ratio, but we will be able to allow that to cancel, because what we'll do is we'll essentially take as a ratio the two profit functions. So differentiate this for now. Just on a simplistic basis, and thinking of this as total talent, which often we take as fixed in a sports league. So we could just say that that is big T, for a fixed amount of talent. That said, if we do that, we're going to end up with nothing in terms of nothing to work with, because if we differentiate this with respect to Ti, and we say that that's not, we ignore the fact that Ti is in the denominator there, we do have a slight problem, because just to make it clear, d pi I dti. Well, in that case, this just disappears. We're left with phi mu I minus c, which is an expression, but it doesn't tell us anything about these anything about what the optimal talent ratio is, which is kind of the idea of this analysis. Okay, so we're going to think about this not as t. We're going to think about differentiating as well. Just to make it clear, we'll call that ti and tj, just so that we know that we're differentiating ti. So we'll put a scribble through that as well, because that's not treating the t on the denominator as part of the whole expression, and we need to do that. I personally, I've always been someone that likes to differentiate with the product rule rather than the quotient rule, just a matter of comfort, so I'm going to rewrite this so that I'm happier differentiating it. It's going to be a little bit messy, but things will cancel. That's ti plus tj to the minus 1 minus cti, and we're going to differentiate that with respect to t. So again, d pi I dti. Do the first expression here, and we've got two terms involving ti, so we do the first, leave the second, plus leave the first, do the second. So do the first, leave the second, phi I mu I ti. Sorry, no ti because it goes, but we're left with the thing on the bottom, ti plus tj to the minus 1. So let's do the first, then so do the first, leave the second, leave the first, do the second, plus phi I mu I, leaving the first, so ti stays, and then this thing here, ti plus tj to the minus 2, and the minus 1 comes down, so that is all minused. Then minus c equal to 0 because we're maximizing. So it's messy. But at this stage, what we can do is we can, hopefully we will be able to start to get things cancelling out. It's often helpful to have in mind what the final expression that we're looking for is, and in this case it's equation 8 in the slide, so we'll just write that up here. We're looking for t1 over t2, I put an I there, t1 over t2 equal to mu1 over mu2. And the way in which we get that is we say, well, one way in which we can get that is we can look at expressing the objective functions of the two teams in the league as a ratio of each other, putting them equal to each other in one way or another, and we can put the two equal to each other. But let's first of all tidy this up a little bit first. Make it look a bit better. Phi I mu I over ti plus tj minus phi I mu I ti plus tj minus c equals 0. Okay, so what might we do in this situation? Well, we can start thinking about making it a bit simpler by multiplying through by ti plus, no sorry we can't because there's a squared term there. I mean, we could still do it, but it wouldn't solve the fact that we've got quite a lot of stuff. Okay, if you're wondering what happened there, I thought I'd just pause rather than try and blunder my way through the maths. It's better. One thing that my dad always taught me, he was a maths lecturer, was don't do maths on the fly, and this was a little bit of doing maths on the fly. It usually goes wrong in front of a class, it goes wrong in front of a video camera as well. What do we do from here with this expression? Well, what we can do is we can try and tidy it up a little bit, and so we can factorize out, so we can take out phi I mu I ti plus tj, because that's what this is, and there's a phi I and mu I and at least one ti plus tj on the numerator there. So then that's open brackets 1 minus what's left, ti over ti plus tj. Multiply that, you'll get it squared, and you'll get your numerator term. We take c over to the right hand side, and we'll see why in a moment. Okay, but what we can do now is we can think about this term here. This term, well, that is ti plus tj, because that's equal to 1. numerator and denominator cancel, Ti plus Ti plus Tj, which is equal to Ti plus Tj minus Ti over Ti plus Tj, Tj over Ti plus Tj. So therefore this term is now phi I mu I Tj. We can just write it out, we might as well. Tj over Ti plus Tj. So in other words, phi I mu I Tj over Ti plus Tj squared equal to C. Where are we with our numbering of equations? We've kind of lost the plot, haven't we? I've lost the plot of... there we go. Right. I put that on that side, didn't I? So 11, we'll say that was 12, 13, 14. It's really handy when you're doing these kinds of mathematical expressions in an assignment, in an exam, to number the equations as well. It just helps you to refer back to things. We'll call that 18, and we'll go on to the next page. Now, we're looking at the generic case, Team I. Of course, we've got Team 1 and Team 2. That's what we want to think about. So let's turn it into Team 1 and Team 2. For Team 1, we have phi 1 mu 1 T2. T1 plus T2 equal to C. And we've got Team 2. And their profit maximizing condition is phi 2 M2 T1 plus T2 equal to C. These are the profit maximizing conditions. Both teams are profit maximizing, so a way in which we can get an expression for what happens in the industry as a whole is we put these two profit maximizing conditions equal to each other, set them equal to each other. And how do we best do that? Well, we use the fact that we've got C on the right hand side of each. So we use the C to put these two equal to each other. So we could say that's 19 and 20, so we'd say 19 equals 20 gives us phi 1 mu 1 T2 over T1 plus T2 equal to phi 2 mu 2 T1 over T1 plus T2. Note that I forgot about the squared terms. And then things cancel. Things cancel in terms of this stuff on the bottom cancels. T1 plus T2 squared cancels on both sides. This is with phi 1 mu 1 T2, phi 2 mu 2 T1. And then we can get the ratios that are in our lecture slides if we make one final assumption, which is that the phi function is equal for each team. Both teams are able to extract the same amount of utility. Okay, but first of all, what we've got in the lecture notes, we've got T1 over T2. So let's take T2 over to that side. T1 over T2. And we'll take these two, phi 1 M2 down to that side. T2 is going to that side, so that we then have phi 1 mu 1 over phi 2 mu 2. The lecture slides, and I presume therefore Szymanski, I haven't checked recently, must assume phi 1 equal to phi 2. Teams extract same monetary value from utility, from farm utility. If that's the case, then we have our ratio, our desired ratio. Then then M1 over M2 is equal to T1 over T2. which is what is in the lecture slides. Again, this tells us that if fans of Team 1 are more intense, well then, equally, it must be the case that T1 is greater than T2, because this will be greater than 1, and this has to be greater than 1. Okay? If that's the case, then remember that the win ratio is T1 over T1 plus T2, which will be greater than a half. If T1 is equal to T2, that will be a half. But when T1 is greater than T2, it's greater than a half. So again, we could have a, we may well have that there's a imbalance, competitive imbalance, and that's profit maximizing competitive imbalance dependent on how intense fans are. And of course, you might think, therefore, it's optimal for wealthy people to set up sports teams in areas where fans are more intense. And you can think about this perhaps in the context of North American sports and franchises, where owners might want to then move their teams to where fans are more intense. What about the relationship between the social, the profit maximizing condition, which is 21, we're going to call it, and way back our optimal condition under utility maximization, which was expression 11 here? Will they be equal? When will we get something similar to this? Well, the answer is we get it essentially by chance. If it so happens that teams are equally intense, their fans are equally intense, well then we have the equally, we're going to have that T1 is equal to T2, which is going to tell us that the win ratio is T1 over T1 plus T1, which is a half. And if W1 is a half, W2 is 1 minus W1 is a half as well. We need to really set that out. But equally, from 11, in this situation, mu1 equal to mu2, the socially optimal outcome is a half as well. Okay, so in that case, we do get equality between the social optimal outcome and the profit maximizing outcome, but only in that situation. And the final tagline to say is that, well, we can have competitively imbalanced leagues that are welfare optimizing and also that are a result of teams profit maximizing as well. And this has implications when we think about reforms that we think would be take a league away from being profit maximizing. Most sports fans don't like sports clubs to be profit maximizing, but reforms that take leagues away from that won't necessarily lead us to a more equal outcome. So that's that. So I'll leave that there, and I'll take pictures of all these slides so that you can make use of them with your consideration of these mathematical models.